All right, yeah. Hi, everyone. So I guess it's our last time in person for this paper. So the point today is to finish abstraction of Jordan canonical form. We want to show that every linear operator whose characteristic polynomial splits has a Jordan canonical form. This was the aim all along, right? Okay. So let me remind you where we are. So we have demonstrated. Well, we have proved a couple of theorems already towards it. In one of them, we have proved that if we are able to find the basis for each generalized eigenspace k lambda, given by a cycle of generalized eigenvectors, then we can put them together in order to form a basis for the whole space, which would give us a Jordan canonical form. Okay, so now the task is then to show that each k lambda has an ordered basis, which consists of a union of disjoint cycles of generalized eigenvectors. So let's prove this. This is like the key remaining step. Okay, so this is going to be theorem 7.7. Okay, theorem 7.7. So we let T be a linear operator on V, where V is, as usual, a finite dimensional vector space. Yeah, so the dimension of V is finite. And assume that lambda is an eigenvalue of T. Okay. So now we want to look at the eigenspace, generalized eigenspace, corresponding to lambda. So then k lambda, the generalized eigenspace corresponding to lambda, has an ordered basis consisting of a union of disjoint cycles of generalized eigenvectors corresponding to lambda. Just a small warning here. We are not saying that there is just a single cycle which gives a basis for k lambda. Yeah, we are only saying something a bit weaker. We are saying that there is a disjoint union of cycles which gives a basis for k lambda. So it might be more than one that you have to take. Okay, so this is the theorem. Let's prove it. So for the proof, it's natural to proceed by induction on the dimension of k lambda. So we will argue by induction on n, which we take to be the dimension of k lambda. Okay, so the dimension of the generalized eigenspace corresponding to the eigenvalue lambda. The base case is n equals to 1. Okay, this is the base case. So in this case, there's nothing to do. Okay, because it's clear because we can take any x non-zero in k lambda. Right, it must exist. And then the set consisting of the single value x, yeah, just a single element set x, is a cycle of length 1. Right? Remember, all cycles look like a generalized eigenvector x, which is the nth vector of the cycle, and then we have t minus lambda I to the power 1, then to the power 2, etc. Until we get the initial vector of the cycle. So a one element cycle is trivially a cycle by definition. And so this is a cycle of length n, 1, excuse me, well, n is 1 in this case. And it is, of course, a basis. Yeah, so and a basis for k lambda, because k lambda is one dimensional, we're assuming. So any non-zero vector gives a basis. All right, so the case n1 is trivial. So now let's argue the inductive case. So assume now that the dimension of k lambda is equal to n strictly greater than 1. Yeah? So 2 or more. Okay. And assume that the result already holds. Whenever we have that the dimension of k lambda is less than n. Okay, and the task is to prove then that the theorem also holds for k lambda of dimension n. So the idea here is a bit similar to what we did in the proof of the theorem 7.6 in the last lecture. So we want to look at the linear operator u, which we take to be t minus lambda I, and we restrict it to k lambda. Okay, so this is going to be a linear operator. So then we have that u is a linear operator on the space k lambda. So first of all, remember it makes sense to look at this restriction because k lambda is a t invariant subspace. We proved this at some point, right? The generalized eigenspaces are invariant subspaces. And of course, the identity operator is also, well, k lambda is trivially invariant for the identity operator. And so this whole operator, t minus lambda I, the space k lambda is invariant with respect to it as well. Yeah. So then it makes sense to talk about this restriction. So we denote it by u. And like in the last proof of theorem 7.6, we want to look at the range of this operator again. Because when we look at the cycles, how are they generated? They're generated essentially by applying this operator some finite number of times, right? Like to get some power p. That's why like it makes sense to study the range of this. So let's look at the range of u. The range of u. Of course, it's automatically a subspace of k lambda. Space of k lambda. So this is always true, right? Because k lambda, sorry, u is a linear operator on k lambda. So of course, the range is a subspace of k lambda then. And the non-trivial claim is that the range of u is in fact not all of k lambda. Okay, so we don't get all of k lambda as the range of u. So why this? So let's check it. So indeed, assume towards contradiction that R of u is equal to k lambda. Yeah. So the range is the whole space, subspace k lambda. Then take any x0, which is not equal to 0, in k lambda. Okay. Then there exist vectors x1, x2, etc. In k lambda, such that we have x0 is equal to u of x1, which in turn is equal to u square of x2, which is equal to u cube of x3, etc. Yeah? Why is this possible? Again, look, we're assuming that the range of u is the whole subspace k lambda, right? So then it means if I take any vector in k lambda, it's the image of some vector in k lambda. So let that vector be x1. Okay, but now x1 again is a vector in k lambda. So it is in the range of u. So there exists some vector x2, so that u of x2 is equal to x1, etc. Right? So we can continue building a sequence like this. And additionally, in this sequence, all the vectors are going to be distinct. So we, well, distinct at least not equal to 0 more precisely. So and we have that xi is not equal to 0 by linearity of u. Right? Because remember, we're assuming that x0 is not equal to 0 and u is linear. So it means it cannot send something else to 0 here, right? So we have this is not 0 as well. Similarly, x2 not 0 as well, etc. So we get that xi is non-zero. because otherwise it would have to be sent to 0, just by linearity of u, right? Okay, so each of these vectors is non-zero, but this means that we have xm plus 1 is in particular not in the null space of u to the power m, yeah, where m is the multiplicity of lambda. Right? Because I mean, we can find xi like this for any I. The sequence can be continued for as long as needed. So in particular, if we take m to be the multiplicity of lambda, just some finite number, you can take the sequence, generate the sequence long enough so that you have x m plus 1, and it's not in the null space of the mth power of the operator. Because if you apply u m times to it, it means we're just going back down the sequence, right? Like if I keep applying u here, we don't get 0, right? So it's not in the null space if we apply um times. Yeah? Okay, so it's not in the null space of but this is a contradiction to a theorem we proved, right? Because this contradicts theorem. This was theorem 7.2. So remember, this was the theorem which says that for any generalized eigenvector, the power p, so that so that t minus lambda I to the power p applied to it is 0. This power p is bounded by the multiplicity of the eigenvalue. So we proved a theorem like this. But in this case, we get a vector xm plus 1, which is in k lambda. So it is a generalized eigenvector in k lambda, and the multiplicity of lambda is m, but it's not 0. Applying, taking the nth power of t minus lambda I, applying it to this vector, we don't get 0. So this contradicts the theorem. Yeah. Okay. So this shows that our premise was wrong, right? So we started with this assumption that the range is everything, all of k lambda, and we have proved that this gives a contradiction. Okay. So this contradiction shows that indeed the range is not all of k lambda. So it's a proper subspace of k lambda. And remember, we know that if you have some subspace of another subspace and they're not equal, then the dimension has to be smaller, strictly less. Yeah. So then we conclude. Well, let me write it on the new page. So the conclusion of this is that the dimension of the range of U is strictly less than the dimension of k lambda, which is n. Again, we know, right, that the dimensions of the generalized eigenspaces k lambda are just the multiplicity of the eigenvalue lambda. So we get that the dimension is smaller, okay? This looks promising because we're trying to use the inductive assumption. So we found some subspace which seems to be related to the question, and it has a smaller dimension. Okay, so the dimension is strictly less, and we also have that the range Ru is the space of generalized eigenvectors corresponding to lambda, restriction of T to the range. So we have that this is smaller dimension, and it is the space of generalized eigenvectors corresponding to lambda for the restriction of T to this subspace Ru. And so this means we can apply the induction hypothesis to this situation. Yeah. So applying the induction hypothesis, to T restricted to the range of U, and well, enter U, which is of smaller dimension, we conclude that there exist disjoint cycles. Let's denote them as gamma 1 through gamma q for some finite number q. So there exist disjoint cycles of generalized eigenvectors of this restriction, so of t restricted to Ru. Yeah. So that moreover, since they are generalized eigenvectors of t restricted to some subspace, they're also generalized vectors of t itself, of course. Right? Remember, we know this for the usual eigenvectors. The same is true for generalized eigenvectors. If you restrict t to some subspace, it does the same thing as t does on this subspace, right? So then if you get 0 for some power, it means you already got off the restriction. You get 0 for the same power of t already. Yeah, because it's just the same thing restricted to a subspace. So in particular of t as well, yeah, generalized cycles of generalized eigenvectors of t as well that we get here, all corresponding to lambda, of course. So corresponding to lambda, so that if we take the union, oops, if I take the union and let's say the union, let's denote the union gamma, which is the union of gamma I of all these cycles from for I ranging from 1 to q. So this is going to be a basis. So it is a basis for U, yeah, the subspace range of U. So we just applied the inductive assumption to the subspace Ru, smaller dimension, and t restricted to it. We found a basis consisting of a disjoint union of cycles of generalized eigenvectors. Yeah. Okay. So we have this for this subspace, and now the task is to somehow extend it to t itself. Yeah. To extend it to the whole space. So this needs some more work. So everyone is okay with this so far? So we found these gammas. Yeah. Now we're going to use these gammas to build a basis with the same property for t itself and for the whole space V that we started with. Okay. All right. So how do we do this? Well, so for each I between 1 and q, so for each of these cycles, gamma I, let's look at the end vector of gamma I. So each gamma I is a cycle, right? So it has the initial vector and the end vector. So the end vector of gamma I is going to be the image under U of a vector, let's denote it Vi in k lambda. Okay. So again, because this is in the range, right? So any vector in the range is the image of some vector in U, in the range of U, I mean. Not in U, sorry, in k lambda. I mean, yeah. Is the image of some vector in k lambda. So let's denote that vector by Vi. And what we claim is that we can extend gamma I by adding this vector at the end. So we can extend gamma I to a larger, okay, sorry, this is gamma I to a larger cycle or set of vectors, but we'll see it's a cycle, to a larger cycle, which I'm going to denote gamma I tilde. So this consists of gamma I and this additional vector Vi, so that U maps it to the end vector of the gamma I itself. Yeah. So we're just adding one more vector at the end to each cycle, which is the preimage of the end vector of gamma I under U. Yeah. So this gives us a cycle of length one more. So this is gamma I, and this is still a cycle of generalized eigenvectors of T corresponding to lambda. So why do we see that this is still a cycle of generalized eigenvectors? Because look, for example, if I had this gamma I, it consisted of some vectors. Like I have some vectors here with x in the end, right? This was, I know, how did I denote it? The end vector. I didn't denote it, but let's say xi was the end vector of gamma I. Okay, so let's look at the end vector here. And now what did we do? So how did we define gamma I tilde? So we take the same, whatever was before. We still have xi, but now we add this new vector vi with the property that xi is given by applying u to vi. So it means xi is given by t minus lambda identity of vi, right? Okay, but then remember the next, like for example, what was the next vector here in this cycle? So the next vector was t, let me write it. It was t minus lambda I of xi, right? But then I can write it as t minus lambda I square of vi, right? Because x is given by the same, by u applied to vi. And I can continue like this for each vector in the cycle gamma I. So the conclusion is that gamma I tilde is also a cycle of generalized eigenvectors with the new end vector vi now, and length is one longer. So it's one has length plus one compared to the length of gamma I. Right? So this so we define gamma I like this for each I, for each of the cycles we had. Okay. And now for each I, again, between 1 and q, we'll let wi be the initial vector of gamma I tilde. So of course, this is the same as the initial vector of gamma I. Same as the initial vector of gamma I. And in this example, so this should be here. So this was wi, the initial vector of the cycle. And we still have it unchanged in gamma I tilde. Okay, so just denote it like this. So now we have a bunch of cycles, all in the subspace range of u. Well, sorry, vi doesn't have to be in the range of u. So it's just in k lambda. So all of these are vectors in k lambda, right? And still cycles. So we have a bunch of these cycles, each of them in k lambda. So the question becomes, is this enough? Yeah. So do these cycles actually work for k lambda itself? So that's what we need to understand. So okay. So denote by w like this, the initial vectors. So now we have that w1 through wq. So these are the initial vectors of disjoint cycles, right? So are the initial vectors of disjoint cycles we also know that they're linearly independent. So this is what we proved last time. This set w1 through wq is linearly independent subset of the usual eigenspace E lambda, corresponding to the eigenvalue lambda. So this uses two things. So the fact that it's linearly independent follows from disjointness of the cycles. This is what we proved at the end of the previous lecture, right? And the fact that this is a subset of E lambda, we observed it earlier. I don't think there's a number for this property, but this was one of the first things after the definition of generalized vectors. Because remember, if you take the initial vector in a cycle of generalized eigenvectors. This means that applying t minus lambda I to it once again, we get 0, right? Because the length of the cycle p is chosen smallest, so that you get 0 if you apply this operator t minus lambda I p many times to it. So the initial vector, if you apply t minus lambda I once again to it, we get 0 by definition of the cycle. Yeah. So this means that, but if you get 0, applying t minus lambda I to some vector, this means that this vector is an eigenvector corresponding to lambda, the usual eigenvector. That's how we see that this is also a subset of E lambda. Okay, this okay with everyone? All right. So this is so it means we have a bunch of usual eigenvectors here. So let's see how this helps. So if we have a subset of an eigenspace, we can always extend it to which is moreover linearly independent here. This means we can extend it to a basis for this eigenspace. Yeah, just a standard 115A business. So so this is linear independent. Okay, so let me write it carefully. So since this set W1 through WQ is a linearly independent subset of E lambda. Okay, how do I say it? So let's say hence this can be extended. The set can be extended to a basis for E lambda. Right? So a priori there might be more, the dimension of lambda might be bigger than Q in this example, but we can also extend it to a basis. And let's write this basis as follows. So it starts with these vectors W1 through WQ that we already given. And then we just add some more vectors, which I'm going to denote as U1 through US. Okay. Because again, the dimension of a lambda might be bigger than Q. So we might have to add some vectors in order to get a basis. So I just denote them like this. And of course, it's a finite least because everything is finite dimensional. Yeah. So in particular, E lambda is finite dimensional. Okay. So we got the basis for E lambda. Then we look at the following collection. So I have gamma 1 tilde, gamma 2 tilde, etc., gamma q tilde. So these are all the cycles I already have. Yeah. And I add several cycles consisting of a single vector. So I add U1 through US. Okay. So these are all disjoint cycles. Of generalized eigenvectors of T corresponding to lambda. Okay. So again, remember, if I have a real eigenvector, an actual eigenvector, it gives me a cycle of length 1 automatically. I just have to take the vector itself, the eigenvector itself. That's how we see that each of these is a cycle. So these are all cycles of length 1. Yeah, so all cycles of length 1. And gamma 1 through gamma q, these are cycles I already had before. So I was given. Yeah. So this okay. So we have this list of cycles. Now, why are they? Moreover, we have such that their initial vectors are linearly independent. Right? They're linearly independent because, well, from the construction. So we knew that because they all form a basis for E lambda. So they are in particular linearly independent. Yeah. I mean, this set, because this is precisely the set of the initial vectors of all the cycles. Yeah. If a cycle is of length n, if a cycle has length 1, then the only vector in it is both initial and end vector simultaneously. So these are all of the initial vectors of these cycles are linearly independent. Okay, but in this case, we can apply a result we proved earlier. So hence, we have that if I take gamma tilde to be the union of all of this stuff, so gamma 1, union gamma 2, etc., union gamma q tilde, and these vectors u1, us. So I take the union of all of this. Yeah. So all of this is a linearly independent subset of k lambda. And this is by theorem 7.6. Remember, we have a theorem which says that if I have several cycles of generalized eigenvectors, and the initial vectors are linearly independent, then all vectors in the union are linearly independent as well. So this was theorem 7.6, right? So this means that linear independence leads from knowing the linear independence of initial vectors to linear independence of all vectors in the union. Yeah. So this is again theorem 7.6. All right. So we have this linear independent subset of k lambda. Okay. Now we are done choosing vectors. So what remains is to prove that this is a basis. Yeah. So the claim is that this gives a basis for k lambda. So we claim that this is a basis. Well, let me say it more precisely. So gamma tilde is a basis for k lambda. Okay. So this is a basis, and if we can show that it is indeed a basis, we would be done, because it is a union of disjoint cycles of generalized eigenvectors for t by construction, right? Because each gamma 1 tilde, gamma I tilde was, and each of the ui also gives a cycle for t. So if we can show that gamma tilde is a basis, we are done because it satisfies the requirement. All right. So let's show this. So proof of the claim. Proof of the claim. So suppose gamma consists of R, which we take to be the rank of U vectors. Okay, so let's denote the dimension of this by, let's denote the size of gamma by R. So we know that gamma was a basis for the range of U, right? So it means the size of gamma was exactly the rank. So note, this is not gamma tilde, this is gamma, the basis we had initially for the range of U. Yeah. So denote this by R. Okay. Then by construction, gamma tilde consists of R plus Q plus S vectors. Okay. Because we have, yeah, this is again, let's remember where all these numbers come from. So Q was the number of vectors in W1 through WQ, right? So this was the initial vectors of the cycles. And S comes from this completion of the basis. So when we had to complete the basis for E lambda, starting with W1 through WQ. So if we look now simply at the definition of gamma tilde, we see that it consists of these many vectors. Okay. So we get gamma tilde consists of R plus Q plus S many vectors. Okay, and as we have W1 through WQ, U1 through US is a basis of the eigenspace E lambda. This is by definition, right? But what is E lambda? E lambda is simply the null space of U, right? It's just the definition of eigenspace and U. Yeah? So E lambda is literally the null space of U, and we have the range also. We know the dimension for the range, the rank of U. So we suggest maybe we can use the rank nullity theorem, right, for U. So we have that nullity of U is equal to Q plus S, right? Because R is the rank, so nullity is Q plus S. Okay. So because all of this are in the this is a basis for the eigenspace E lambda, which is the null space of U, right? So this is so this tells us the dimension of E lambda is Q plus S. All right. So now we use rank nullity. So we have that the dimension of K lambda is equal to the rank of U plus nullity of U, right? So this is going to be R plus Q plus S. Okay, but now look, we have two things. So we have the dimension of all of K lambda is given by R plus Q plus S, right? But also the size of gamma tilde is the same, R plus Q plus S. Yeah, and gamma tilde is linearly independent. So this we know, right? Gamma tilde is a linearly independent set. So we found the linear independent set of full dimension. So it is a basis. So this, so we conclude that gamma tilde is a basis for K lambda. And this concludes the proof of the inductive step. So we have found a basis for K lambda consisting of disjoint union of cycles of generalized eigenvectors. Well, anything in K lambda is a generalized eigenvector, except for 0, yeah, by definition of K lambda. So we found a basis consisting of these cycles. So this proves the theorem. This proves theorem 7.7. And now we are all set to, to finish the main task, yeah, to find the canonical Jordan form for an arbitrary operator whose characteristic polynomial splits. So now we're just going to combine all that we know up to now and see that how the result comes out of it. Yeah, let me pause here maybe for a second. Is there any questions? Let me see. Anything online? No. Okay. All right. So then let's do this. So let's finish the task. So this is going to be corollary 1. Maybe not not sufficiently pompous name for the main theorem here, but it's corollary because it follows by combining theorems we proved already. Somehow we already did the hard task. Yeah, but you know what? Let me call it the theorem. I mean, this deserves. I think, if anything, this deserves a name of a theorem. So assume T is a linear operator on V. Finite dimensional as always. And assume that the characteristic polynomial of T splits. Yeah. So our one assumption. And just to remind you again, so this is if we are working, for example, with the complex numbers, then this assumption is trivial. There's no assumption. Yeah. So if the field of scalars is the complex numbers, this means this can be an arbitrary linear operator over the complex numbers, because the characteristic polynomial splits automatically by the fundamental theorem of algebra. Okay. So then T has a Jordan canonical form. Okay. This is the theorem. Proof. So, okay, so it's finite dimensional. So we can list the distinct eigenvalues. So we have lambda 1 through lambda k. Let this be the distinct eigenvalues of T. Okay, there are finitely many of them. Now, for each of these eigenvalues, we can use the theorem we just proved. So by theorem 7.7, for each I between 1 and k, there is an ordered basis let's call it beta I, consisting of a disjoint union cycles of generalized eigenvectors of T corresponding to lambda. So theorem 7.7 guarantees that there is a basis for k lambda. I mean, okay, this is just so for, in other words, for k lambda. Yeah, so we have a basis for k lambda consisting of such cycles of generalized eigenvectors, a disjoint union of them. All right, but then we let beta be the union of all this beta I. This should be lambda I, excuse me. And this is k lambda I. Yeah. So I just apply this previous theorem. So I fix I fix one eigenvalue, lambda I, and I apply the theorem with respect to k lambda I for this particular eigenvalue. Then I do it for each of them. Yeah. And then I take beta to be the union. So beta 1, union beta 2, etc. Union beta, what was it, k? Yeah, we have k many. All right. So I take a union of bases like this, but we already know something by early results again. Yeah. So by theorem, this was theorem 7.4b. This union beta is an ordered basis for V. For V. So do you remember the statement of this theorem? Should I remind it? So what the theorem says is that if I have, well, it literally says what we are doing here. Yeah. Like if I have, remember the theorem says that if beta I is a basis for k lambda I, yeah, where these are all distinct eigenvalues, then taking the union gives us a basis for the whole space. So the point was that the whole space is the sum of the generalized eigenspaces. Yeah. So then we have that union beta I, where over all distinct eigenvalues of T is a basis for the whole space V. Basis for V. So the theorem literally fits here perfectly. It tells us that if I take the union of the basis for each of the k lambda, I get a basis for the whole space. Okay, but this basis is also not arbitrary, of course. So by theorem 7.5b, we get that beta is a Jordan canonical basis for V. It's a basis for V, and it's given by a union of bases for each of the k lambdas. And we know by that theorem 7.5 that matrix corresponding to each of the beta i's, representing T restricted to each of the beta i's, is a Jordan canonical block, right? And so the union is going to be a Jordan canonical basis, which then gives us matrix. Well, if you take matrix representing T with respect to this beta, this is a Jordan canonical form, because beta is a Jordan canonical basis. Yeah. So this is it. This concludes the theorem. This concludes the proof. Yeah. So great. I mean, I think this is the last theorem of the course. The main theorem, it uses all the ideas we have studied, which were a lot. Yeah. We studied the, well, you see, everything is used here. Invariance of spaces, eigenspaces, cyclic subspaces, anything you can think of. Everything comes into play into the theorem. And yeah, so but it tells us that we have this, we generalize these ideas, which are already non-trivial in the case of diagonalizable operators, that you can then get a diagonal matrix. For such operators, we generalized it to a much larger class of operators. So it took a lot of this extra work, but yeah, but then it's a much more general theorem, a much more powerful theorem. So unfortunately, we don't get to see many applications of the theorem in this course, but like I guarantee you, if you'll see it again somewhere. Like if you ever study more math, or not even just mathematics, like in physics and computer science, everywhere it arises. So you'll see that is, you'll know for the future, like it's a powerful theorem. Yeah, you probably will see it somewhere. Yeah, I guess, yeah, so I'm gonna stop here. Thank you very much.